G'day guys, welcome to lecture 6 of topic 2, gravity. Here are your learning intention and success criteria. Please complete the KS table. Pause the video while you complete this. Okay, now hopefully looking through here, we identified a couple of things for knowledge. Firstly, we need to know what are gravity and gravitational fields. We can see that in the what we're being able to explain, and we can see that in the define cognitive verb there. A second bit of knowledge that I hopefully picked up is that through this identify, we need to know what these things are and why do they even matter, because we're going to need to tell the difference on these types of problems. In terms of skills, we have our skill there, calculate, solve, so that verb comes up, can I solve gravity related questions here. Okay, so when we think about gravity, what sort of things come to mind? Now, the very obvious thing from our learning this year would be the force that pulls you and I to the ground. If it wasn't for the seat under our butts, this force would pull us to the floor. Perhaps you're on a second story, so if not for that wood or concrete under your feet, your next stop is going to be the ground a couple of meters below. And this is our everyday truth, that things fall down. And this is what people thought was the truth. And the general wisdom back until the 1600s. No one thought of forces pulling objects towards the earth. It was just things just did it. They just went down. They also assumed heavier things fell faster until Galileo tested it, as we talked about. And remember, so you need to be testing assumptions. And they found from that acceleration was independent of mass. If you read chapter 4.1, it talks about these ideas in a little bit more depth, and it's certainly well recommended. But if we go back to thinking about gravity and you think larger scale, you may recall learning about the planets and stars in junior high and how they're held into orbit by gravity. This is also true. And we'll talk about Kepler and his laws of orbit in our next topic. But what you might not be thinking about is the force of attraction between you and the screen that you're watching, whether it's your phone or a monitor, between you and the chair that you're actually sitting on, between you and everything and everyone around you. Now, we define gravity as the force of attraction between objects with mass. It means any objects. If it's got mass, it attracts anything else with mass. And the other big thing is it's only ever attraction, it is never repulsion. So this is actually reasonably important about gravity, because we'll be learning about some other forces over the coming year, a little bit about nuclear forces later this year, and then electromagnetic forces in next year's topics. We will see that this is not the case, that sometimes these forces can push or pull. But in this case, gravity, as far as we know, can only attract. Now, Newton worked out the proportionality for gravity like we did in class using our simulations. If you missed that lesson, the simulation is available online for you to download and have a play with. And then scientists worked out the constant we call big G in about 1798 using some torsion on wire, and the textbook explains this process. This is the equation that we'll be using here. And we can see here that the force of gravity, Fg over here on the left, depends linearly on our mass 1 and our mass 2. So this means if mass increases by 2, force will increase by 2. If mass number 2 increases by 2, force will increase by 2. But if both masses double, then we have 2 times 2, which is an increase of times 4 in terms of the force of gravity. Okay, so each mass is independently linear, but together they can make quite a change. On the bottom there is a radius term, but note it is squared, so it's not an inverse, it is an inverse squared relationship between force and radius. So this means that every time radius is doubled, the force becomes 1/4 of what it was before. Okay? Now, big G here at the front is a constant. It's always big G because little g is used for gravitational acceleration, and we'll see it pop up later in this unit. And that number will be provided on an exam. The value is 6.67 times 10 to the negative 11. And so you can see that by looking at this number here out the front, unless our masses are quite large, this force is going to be quite small, because as we get further apart from each other, it gets smaller and smaller significantly fast. Okay, you need a radius that's pretty close for this not to matter, for these masses not to be huge, just to feel 1 Newton worth of force. So let's have a look at some examples about gravity type questions. Now, these examples come into two categories. These are big distance categories and small distance categories. When we look at the distances between the Earth to the Moon, the Sun to the Earth, these distances are so vast that the size of the objects is irrelevant. The Earth-Moon distance is the order around 10 to the power of 8 meters, while the radius of the Earth is only about 10 to the 6. And you may think, well, 10 to the 8, 10 to the 6, that's pretty close. But this is a 100-fold difference. Yeah, 8 and 6 are only 2 points different, but in terms of powers of 10, that means 2 extra zeros on the end, and that means 10 to the power of 6 is a very small amount of 10 to the power of 8. And in terms of actually looking at the real numbers, you can fit 30 Earths between the Earth and the Moon. In fact, you can fit all of the 8 other planets, including Pluto, in between the Earth and the Moon if we ignore Saturn's rings. So there is actually quite a significant amount of space. To us, on a personal scale, 6 million meters seems a huge amount of distance. That's 6,000 kilometers. You know, that's a massive amount of distance to walk. Okay? Like walking a few kilometers, sure, we can do that in a few hours, but you know, walking 6 million meters, 6,000 kilometers, that is significant. But in space, it doesn't mean junk. Okay, so when we're dealing with interstellar distances between planets, distances between stars, we don't care about how big the object is. It has no effect. Even the radius of the sun doesn't matter unless you're dealing with something that's very, very close. So this is what we call a big distance group. Then generally when you're dealing with planets and moons, suns and stars, all that sort of stuff, the distance between is all that matters. Okay, what you'll see the textbook say that we treat them as a point. In that all we care about is the distance between the centres of each. Small distances, though, are things like Earth to a satellite. Okay, this is a small distance. Satellites are only around 10 to the 5 meters, while the radius of the Earth is 10 to the power of 6. So that means a 10-fold increase. And so if we ignore the radius of the Earth, it will have a pretty significant change. If I keep, basically my personal approach is if the distance between the two objects is around 10 to the power of 2 bigger than the distance, the size of the object, then don't worry about the size of the object. If it's around 100 times bigger, it's fine. So let's have a look at two examples, one for each of these. So this is chapter 4.2, example A. Determine the force of attraction between the Earth, we've got a mass there, and the Moon. Again, another mass there, given that the Earth-Moon distance is 3.8 times 10 to the 8. If we were to include the radius of the Earth on this, that means we would change that 3.8 to around 3.86 times 10 to the 8, which is not going to be a significant difference. It's less than 10%, or around 5% of a change there. In fact, a little bit less, so it really doesn't matter. So, our force of gravity equation that we've just seen, Fg equals m1, m2, r squared, and we have a g here out the front. So, when we do calculations with this, let me just adjust that a little bit since it tilted a slight amount. Apologies. There we go. So, our m1, let's just make that the Earth. 5.97 times 10 to the 24. M2 is going to be the Moon. 7.35 times 10 to the 22. And it doesn't matter which we make. You could make the Earth the Earth M2 and the Moon M1. It really doesn't matter. And R equals 3.8 times 10 to the 8. So we can just substitute our values in and have a go. 6.67 times 10 to the negative 11 times 5.97 times 10 to the power of 24 times 7.35 times 10 to the 22 divided by 3, what happened there, 3.8 times 10 to the 8 all squared. Now you have to be very careful with the square there on your calculator, because if you do the what's the word I'm looking for? If you don't do this square properly, what you're going to end up doing is going this times this times this, because you can do that all on the top line, divide it by this, and then square the whole thing. Okay. One thing that I think is really important is that you do a bit of quick mental math to see what this answer is going to about be. That way you can double check your calculator a bit easier, because remember, calculators are stupid. They do exactly what you say. So if I have a look at the numbers here, I have 24 in power 10 to the 22. So it's going to be 46. 10 to the negative 11 there is going to take that away from that, so that will drop my 46 down to 35. If I look at the numbers though, I have a 6 times a 5 times a 7. 6 times 5 is 30, 30 times 5 is 210, so that's going to increase my power by another 2, so that means 24, 48, 48 take away 11 is 30, so what did I say, 48, 37. And then on the bottom here I have 8 squared, so 8 squared is 16, 37, and remember when we divide by power we subtract it, so 37 take away 16 is going to be 21, and we're going to divide by 3.8, so it's probably going to cancel this 3 down to a 2 here, so we're probably going to end up around power 10 to the power of 20. So I'm going to put this here off to the side, about 10 to the power of 20. You don't have to be really super accurate. For example, if I could have just gone 24, 22 is 46, take away 11 is 35, take away 16 is 19, and I could have written that, and would be, again, if I'm within 1 or 2 powers of 10 of it, that's within a rounding error, ignoring those numbers there, so I'd be pretty happy with that. Let's chuck that into the calculator. 6.6 times 10 to the negative 11 times 5.97 times 10 to the power of 24 times 7.35 times 10 to the power of 22. That's giving me a power of 37 on the top, divided by 3.8, 10 to the power of 8 squared, close bracket, gives me 2.03, sorry, 2.03 times 10 to the power of 20. So my approximation was pretty spot on. This is a very good thing to be doing, because you are not going to be very familiar with the numbers you're going to be working with on this, and you need a way to check. Okay, so this is for big distances, distances between moons and planets and stuff like that. This is an example of a small distance problem. Determine the force of gravitational attraction between the Earth, look at the mass there, and a 72 kilogram physics student when the student is in an airplane of 10,000 meters, which is 1 times 10 to the 4. The radius of the Earth is this. Now, interesting thing of note here. The radius of the Earth is not a value in your data booklet. So, I'm actually going to email Mr. Roach about this to ask whether or not it's something that I expect you to memorize or not. I will check the syllabus, but I don't believe it's mentioned in the syllabus as a student should memorize this number. As such, if the question specifically tells you, remember, the radius of the Earth is this, it's a pretty good clue you're going to need to use it. That being said, all questions about Earth distances might end up having it mentioned as a false herring. We don't know. So you may sort of consider it as a, perhaps I need to use this, but maybe don't take it as a hard and fast rule that if it's there, definitely use it, because it may not be something that you need to be doing, and you might actually end up getting marked down if you don't recognize when to use it or when not to use it. Remember the rule: if it's within about a power of 100 or so of, so 10 to the power of 2 of each other, then it's probably worthwhile using it. If not, not worthwhile using it. If it's within 10 to the power 1 or anything smaller than itself, definitely use it. And 10,000 meters here is definitely smaller than the radius of the Earth, so we're definitely going to end up using it. The good news is, the questions that use it versus the questions that don't use it are going to be pretty distinct. So, same thing as last time. Our M1, in this case, let's make it M1 equals 72, M2 equals 5.97 7 times 10 to the 24. We have r equals 6.37 times 10 to the 6 plus 1 times 10 to the 4. So let's see, if that's 10 to the 6, that's going to be 10 to the 5, that's going to be 10 to the 4, so it's going to add to this value, 6.38 times 10 to the 6. You can see here, if I was to divide by 1 times 10 to the 4 compared to 6 times 10 to the 6, this number here is going to be significantly larger than that squared. So that's why this is so important. We know our force of gravity formula. Fg equals g m1 m2 over r squared equals 6.67 times 10 to the negative 11 times 72 times 5.97 times 10 to the 24, all divided by, 6.38 times 10 to the 6 squared. Again, let's do a quick approximation. 24, that's a power of 10, that's a 10 to the power of 1, so it's going to be 25. Take away 11's down to 14. 6 squared is 12, so it's going to be around 10 to the power of 2-ish region. These numbers are probably, so that 6 and that 6 is going to probably cancel it, so it might be 10 to the power of 3, but we'll see what it comes out as. So 6.67 in negative 11 times 72 times 5.97 e24, so that's power of 16 on the top, divided by 6.38 e 10 to the power of 6, square that, close answer, gives me 7.04 times 10 to the 2 newtons. So 704 newtons between the Earth and this kid floating around in space. So it's a fairly small amount of force compared to what we saw before, even though it's a lot closer because the mass is so much lower. So the other aspect of gravity that you're going to need to understand from the text is what's called a gravitational field. Now I've got here the definition for a field, and it's reasonably abstract. So when we talk about a field, we mean the region of space around a body in which there is a force. In this case, we're talking about gravitational fields, so we're talking about gravitational forces. So around you have a gravitational field pulling things in towards you. The Earth has a gravitational field pulling things in towards that. The Sun has a gravitational field pulling things in towards that. You may have seen those pictures of stars kind of sitting in a nestled grid where it's being pulled down. And this is a kind of a way of representing fields. The good news is we can easily visualize fields in magnetism and sort of see what it looks like. So we can see here we've got our North Pole and our South Pole, and you can see the filings look to trace a path from one pole to the other. So you can see here that they arc, and as you go further away, it arcs more and more. It's quite a larger arc around that point until eventually where it looks like it just curves off and doesn't actually come back around. It may very well come back around, but the image certainly shows that it's a very, very large. So it might be something like that, or something like that. Okay, but probably a lot further down this way compared to what I just did there. I really love this for visualizing magnetic field lines. This is a ferrofluid, so this is an ink that has a significant amount of metallic particles in it, and what you can see, they're bringing a magnet quite close to it, and it is changing the shape of it, and what's happening there, the liquid with the magnetic particles in it is aligning with the magnetic field lines like we see over there, but in this case they're quite dynamic and moving around, which is a lovely image. I like this bit here. So now they've got here field lines from this side, and they've got field lines here from this side as well. And you can see that they're reaching towards each other, which is what we're seeing on here, but in this case it's moving a lot more. So, sorry, I'll go back. When we mean a field, I want you to imagine the room around you and that it's cut up into millions of tiny little cubes. And someone is measuring something about each of those cubes, such as temperature. and writing them all down, or perhaps actively recording them, millions of little sensors. And this would be called a field. It would be the information about a volume of space. Sometimes they're scalar because they don't have any direction, such as temperature. Sometimes they would be vectors because they have a push or a pull, such as when we're dealing with electrical magnetic forces, or just pull when we're dealing with gravitational forces. So a gravitational field in this case is a measurement of what the gravitational acceleration is at each point. Now, we say that the field causes the force to happen, and the language that physics uses is that the force is mediated by the gravitational field. In this case means to bring about. Okay, and this is an example of drawing a gravitational field. We can see here we've got a significantly large mass, M, and we have all these field lines running into it with the arrow pointing in towards it. And we can see here that this smaller mass would be feeling a pull towards the larger mass equal to the gravitational field G in this case. All objects, no matter what their mass is, will feel the same gravitational field. We'll see why that happens in a second with the equation. However, their force will be different. Remember that forces do depend on the mass of the object and the acceleration being applied to it. So gravitational field is about the acceleration and it causes the force in this case. Now, because it is defined as force felt per kilogram of object, we define the units as Newton over kilograms, and which means that we can derive an equation where if we take the force of gravity that we learnt Newton's law of gravity and divide it by mass, the mass of the object that we have near our larger object, we end up with this formula to work out G. And this G is the same G that we learnt about doing acceleration due to gravity earlier on. So this G is equal to the force of gravity divided by the mass of the object, which is equal to this equation from before. And you can see that it's the same equation, just there's only one mass term. If I want to know the G for Earth, I'm going to use the mass of Earth. If I want to know the G for Mars, I'm going to use the mass for Mars. If I want to know the little g of Jupiter, I'll use the mass for Jupiter. If I know the little g of the Sun, you get the point. Okay, so you could work out what is the gravitational field strength for around you as well, actually. You would have your own field strength pulling towards you. In terms of the total gravity felt around you, though, not only would something feel the force from you pulling it towards you, but it would also feel the force or the gravitational field of gravity acting down. So we can actually add all these fields together in order to get, well, what is the total field at some point. Generally, you just pick, what are the things that are the biggest, because even with my, gut on me, I'm not going to have a significantly strong gravitational field around me that is really worth measuring when I'm talking about a falling object. So, this equation here is in the data booklet, including this derivation as well, actually. So, if you need to memorize, you don't really need to memorize that, you just need to know how to use it. What's really good is this, again, will allow us to find G for whatever planet, whatever object we care about. So let's have a look at an example here. Calculate the gravitational field strength at a point 10,000 kilometers above Earth's surface and B at Earth's surface. Walding's working for this, I don't actually agree with. Walding's example says that because the point is at 10,000 kilometers, which is well more than the 2,000 kilometers you should worry about for small versus large distance, that it's not worthwhile using the radius of the Earth. I am going to use the radius. In fact, I'm going to do both, with and without the radius of the Earth, because we're going to see what that actually does to it at these distances, because 10,000 kilometers is only a bit under twice as much as the radius. So to me, it still matters. So let's have a look. We need gravitational field strength. The formula G equals big G m over r squared. So what's our m? Our m in this case is the mass of the Earth, which was 5.97 times 10 to the 24. This would be provided to you on an exam, but I'm just remembering it from the previous examples. And we have our radius. So I'm going to do two different radiuses. Radius 1 just equals 6.37 times 10 to the 6. sorry, plus, well, this is 10,000 kilometers, so that's going to be 1, 2, 3, 4, 5, 6, 7 plus 1 times 10 to the 7. That means if I add them together, I get 1.637 times 10 to the 7. My radius 2 is just going to be 1 times 10 to the 7. So that's my 10,000 kilometers without caring about the radius of the Earth. So let's do these two. G1 is going to equal 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24 divided by 1.637 times 10 to the 7 squared. So let's do this one. We get a value of 6.67 e to the negative 11 times 5.97 e to the 24 divided by 1.637 times 10 to the power of 7. And we get an answer of 1.4, let's round that, 1.49 meters per second squared. Now if I change that and I get rid of the 6.37, I'll just turn that into 3 zeros. I'm going to type the whole damn thing in. 6.67 e to the negative 11 times 5.97 e to the 24 divided by 1 e to the 7 squared. If we do it with the other version, 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24 divided by 1 times 10 to the 7 squared, we get an answer of 3.98 meters per second squared. And that to me, I mean, that's almost double. By ignoring the radius of the Earth, we get more than twice an increase in the acceleration. So to me, that's still too close. A 10 to the 7, it's only twice as big in this case. If it was maybe 90,000 kilometers above the surface of the Earth, probably wouldn't care too much then. Wouldn't really be a big deal. But this one is too close in my opinion. So I don't really agree that 2,000 kilometers is the cutoff. To me, if you're not 100 times bigger than the radius, you probably need to consider the radius, okay? And anything, smaller than the radius, definitely consider the radius. Let's have a look at B there. B in this case is, well, what is at the Earth's surface? I'm just going to put up here 3.98, just so that I can have a bit of white space to work for this other one here. So B here is asking, well, what is the gravitational field at the Earth's surface? Now hopefully you can kind of think, well, I've already seen the symbol G, so maybe it's going to be a certain number, and we'll see. Hopefully you've kind of clued into that. So let's have a look. G is equal to 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24. This is all divided by 6.37 times 10, 6.37 times 10 to the 6 squared. Let's chuck it in, and you will get an answer of 9.81 meters per second squared, which is a number that should look very familiar to us. Alright, and so you can actually work out, well, this is what acceleration of gravity should be, and we know because that's what we've been told before in our earlier unit. So, what have we covered? In this video we have covered We've applied Newton's law of gravity to small and large distances between objects, and we have learnt what a gravitational field is and how to calculate G in different situations. Now, for your entrance to class, please access the O-Book and download Chapter 4.2 and 4.3, check your learning PDFs. Complete questions 1 to 5 from Chapter 4.2 and questions 2, 4 and 5 from Chapter 4.3. Copy those into the 2.6 space on eLearn. Remember, this is from the Unit 3-4 text, so you will need to use those other chapters. Alright, thanks guys for listening. Have a good day.